My name is Tanguy Genthon. So I was working at IFREMER until August this year. And so first as a master project with Benjamin and Lucie Boutet, and then as an engineer for 1 year. So I worked on the implementation of Strategy 3 again on the case study of the Norwegian Sea. So first, a bit of context. The Norwegian Sea, is a sea situated in the west of Norway. Here, so I think it's going to be fine. And it's bordered by the Barents Sea on the north, North Sea in the south, and by Iceland Seas, etc. on the west. It's quite interesting. It's a transition zones between the water from the Atlantic, which are warm and saline, and water from the Arctic, more colder and fresh. It's also interesting in terms of bathymetry with two different distinct areas: the Norwegian Shelf, which is quite shallow, 200 to 500 meter depth, and with a slope going quite steeply to the Norwegian Basin, which is like up down to 5,000 meter deep. It's also a hotspot for fisheries, with fisheries being a major anthropic pressure in the area, like a lot of case studies. Fisheries are mostly pelagic, but also a lot of demersal fisheries. So pelagic include herring, and demersal a lot of cod. So we have ICES counts like 19 commercial fish stocks in the area. Those fish stocks, a majority of these fish stocks are being slightly above the fishing pressure since 2005. But however, the biomass is still above the threshold. And for climate, so on the Norwegian Sea, we see important climate variability. That is also due to change in volume entering the water, the Norwegian Sea, so change in the proportion of Atlantic or Arctic water by the year, which creates strong climate variability. It's also a region that is predicted to be quite impacted by climate change. So maybe you saw on the poster of Judy this figure. It's really nice, thanks. Which shows different variables, the different hotspots where you have a significant change between 2019 and 2070 on different variables. And we can see the Norwegian Sea. I'm showing, but I don't know how. Yeah, I have this one. Great. We can see that in the area we have a lot of up to 5 different variables that are expected to change significantly in the future in all the different scenarios. So now, knowing the context, we're going to try to study how will the combined effect of climate change will affect the Norwegian sea productivity and associated fisheries and the future climate scenarios. So our study area, so this is the Norwegian Sea. So this is kind of the inshore zone, which represent the Norwegian Shelf. So with 4 different sediments, a lot of mostly sand, and the offshore zones, which is quite deep. So we decided to represent it mostly by this habitat, which is called hoverhang, that represent in imaginary floating sediment representing interaction with the deep ocean. So here. So we use, I'm not going to present them again, but we use 24 models, so 2 for forcing climate models, GFDL, CNRM, and 2 global scenario, SSP126 and 370, and for 6 different decades. So now on the results. So here we show the productivity, the change in productivity in the ecosystem. So here we have primary production, which is for 2010-2019 for all the different models. So CNRM in blue and GFDL in the red. So this is for primary producers, and we see that I'm spoiling. So we see a decrease, a constant decrease of primary production with time. So here, because we have, forgot to explain, we have here the anomaly of production relative to 2010-2019, and we observe a decline in percent of primary production. And we did this for a lot of different ecosystem components. And we see also for all ecosystem components, we see a constant and a decrease of all ecosystem components, especially for fish. So what we observe also is we have way less difference between the SSPs than we have between the climate models. So we wanted to check what would be the effect of this diminution in productivity on the fisheries. So we looked at the fisheries reference point. So here we have a yield curve. So with catches here and a harvest ratio multiplier. So one means level of fishing we had in the decade 2010, and we can increase or decrease. And in the point here represent the MSY, so the maximum subsuperable yield. And here for pelagic fish in 2010, and with same we can look at how it goes with decades. And for pelagic fish, we predict a diminution of MSY over time, quite a steep diminution too, and also a diminution on the harvest ratio at MSY, meaning we will gain less, and it will be and we cannot fish anymore to have the maximum yield. So we did also the same for demersal fishes, and here we have more contrasted results. CNRM predict quite a steep decrease also in MSY. And a small decrease in harvest ratio, while GFDL predict increase in MSY, but still a decrease in harvest ratio. So we see that the climate change, it does affect, and mostly decreasing the fisheries reference point and the predictability in the future of fisheries. So we wanted to look at what could explain this shift. So of all the different components in all different models going down. As all components are going down, we could estimate that all components are affected. So it's kind of a bottom-up process. So we wanted to look then at the first components of the first trophic level. So we looked at primary production. So here we represent the primary production here over decades. This is for the scenario we used for all different scenarios. And which wanted to see which climate variable had the more impacts. So we decided to fix some of the variables. So here we used we fixed the concentration of nitrates in the boundary condition of the Norwegian Sea, and check if it had an effect on the primary production. It does. It does have a completely different profile than on the baseline sail area. So it shows that this water concentration in the boundary of the Norwegian Sea, or the influxes of nitrogen, have the more impacts. And if we look at all the other different variables, physical, which is in green here, it's also the same profile as the baseline. So what explains these changes in the Norwegian Sea seems to be, at least, the influxes in nitrogen in the area. So we also checked also quickly. I didn't have time to look at it really steeply, but we have if we look at the same result by fixing these boundary conditions and check again at the MSY, we see that it changes completely. We have also a small diminution of MSY, but it's really less than what we had before. And but for demersal fishes, we see an increase in all models of MSY, which means the influxes of nitrogen have an important impact also on fisheries. Yep. Well, so yeah. So what we can remember from this presentation, we have a general decrease in productivity in the Norwegian Sea, also a decline in MSY and harvest ratio at MSY for the pelagic fish and for most scenarios of demersal fishes. And we see that the choice of physical or forcing model have more impact than the scenarios in our results. And we predict that the nitrogen import seems to be the main explanatory variable of this decline. Thanks.
Thank you, Tanguy. Now we have time for questions.
Yes.
Sergio.
Modeling is going up to 2019. Yeah, the real data.
Real data, yeah. We used the data from 2010 to 2019. So
but the question is, we are now past 5 years from that.
Yeah.
And is it going well with the model? The real data from 5 years later. This is just a check.
Yeah, no, it's difficult to say. Like, I don't really know, actually. Yeah.
So thanks a lot. It's very interesting, and I'm curious. So you could show that the model outcomes are very sensitive to the way that nitrogen is flowing or imported into the system. So maybe this question might be more relevant for Yuri, but I'm wondering how good are the underlying climate models or biogeochemical models representing this influx of nitrogen or this import of nitrogen? Because it seems like the responses of the Strathi2E to this is very, very dramatic. So maybe that question is for Yuri, that how well are we resolving these kind of dynamics in the biogeochemical models?
Yeah, I think Yuri is going to be better suited to respond to this question, for sure.
Sorry, Yuri.
Sorry for that.
So a couple of things there. So the first one is we haven't looked into the detail of how good the fluxes are there. What we, in terms of the pattern that we've seen, the model has projected, has been seen in other models as well. So there are consistency in those projections. One thing that we need to be particularly careful, also coming back to what Sergio was asking and your question as well, when we use climate model like this one that we have done for Mission Atlantic, like the one that CIMI provides, the historical period that represent the current data, they have the right statistics, so they can have the average flux that is correct. But if we then want to compare time series of these fluxes, then they might be off sync, for instance, because they have different. So the statistics of the climate pattern are okay, but they might be shifted in time, for instance. So this type of comparison have to be done. Absolutely, I'm not saying that we don't care, and so the model can do whatever. But has always been they have to be interpreted with care in a way, and yeah. So. Can't say exactly. And the other thing is for people like, I guess, you and Benjamin, who know more the area and who know the data availability of that area, because a lot of this information, especially about fluxes, there might not be a lot of also data to compare, especially for nutrient fluxes. There might be transector to assess the water fluxes, and so we could compare that. But then moving from that to the nitrate fluxes, that is the critical there, is even more complicated, I guess.
Some paper estimates an increase of influxes in Atlantic water, which could, in the posterior view, could explain also the decrease in nutrients. But yeah, Benjamin, I think.
Okay. It's a follow-up on Sergio's comment. I think the model fitting is really dependent on the information we have. And in that case, there's quite an interesting situation in the Norwegian Sea for those who don't know. So we get a lot of input from the stock assessments. And this year, the stock assessment for mackerel has been revised, not just with new data, but with actually a new stock assessment model. And the result of that is a doubling of the biomass of mackerel historically. And we are talking millions of tons here of increase in mackerel in the system. So that is a challenge for all the models that have been fitted on historical data in the Norwegian Sea today.
Where does energy come from?
Okay, thank you very much.